objects.
Has two paths. This one is made by black hole, and clearly it takes some time, more time. That means there's a delay in that way. Does that mean that we can observe the same event happening here in two different times in Earth?
Radio waves of the matter that is falling near the black hole. So matter near the black hole, as it gets close to the black hole, becomes dense and hot, and so emits light.
So my question is, are there any research done that assessing the impact of doing research in black holes to their people's life? I mean, what can it give for the people's life, and maybe the impact to the increasing standard of life, or maybe for the future generation? This is very interesting to me. Thank you.
A lot of students and people from outside of the university. I hope that you will enjoy the lecture. So the lecture, I will give you a brief overview of the agenda as well. So we're going to have this lecture roughly 1 hour.
This is what I will be talking about. First of all, I will tell you about how you actually do the observations, how you solve the problem of taking a photo of an object which is millions of years or light years away.
Now you're observing the light coming from the black hole on the ground, on the Earth. Now there might be some gravitating object in the middle between this black hole and Earth's spot, right? Which radiates the light like trajectory or this. I mean, it affects the motion of light. It also affects, I think, that what we say, the image tracing. Yes. This also have been taken into account in the calculations or when constructing the image.
No, but what is more difficult is when you have flaring, in which case what is the flare is the actual emission. And during the flaring we normally don't observe because we cannot model the foreground. But otherwise, if the foreground is known, well, it's easy to subtract it.
A lot of students and people from outside of the university. I hope that you will enjoy the lecture. So the lecture, I will give you a brief overview of the agenda as well. So we're going to have this lecture roughly 1 hour, and then at 2 we're going to have the award ceremony. So I hope to see you as much as possible in the award ceremony. Then afterwards we're going to start the panel session. Please welcome Professor Rezzolla.
How it is possible to take a photo of a supermassive black hole, in particular about M87 and 2022. This is what I will be talking about. First of all, I will tell you about how you actually do the observations, how you solve the problem of taking a photo of an object which is millions of years or light years away. Once you make an observation and you have an image, how you have an understanding, a theoretical understanding of what the image is, and why you believe that image is telling you something about black holes. I will tell you about M87 star and Sagittarius star and the difference between these two black holes, which are quite large, and despite they seem to behave very similar, they are very different in their behavior. And I will tell you about what is it that we have learned in terms of gravitational theory from taking these images. Okay, before I start, we have quite long, but secondly, Sagittarius star is a much more difficult source to handle. So, the observations come with a number of disadvantages and a few advantages. So, first of all, if you think about it, the galactic center is where all the action is. Everybody wants to go at the center of the galaxy. So, there is a lot of things going on. Why, when you observe M87, you're just outside of the galactic plane, here you have to look across the galactic plane. So you're going to collect all the dirt and the rubbish or emission that is between us and Sagittarius star is 10 minutes. So you can go around with a spaceship around Sagittarius star, and in 10 minutes you've done it all. In the case of M87, it took a day, because it's much bigger. So this means if there is something that is flaring, then we can easily see this flaring at different wavelengths. We can also see, just to give you an example, this is the same simulation, but this is when you calculate what it would look like at this frequency, 1 in 30 gigahertz. This is at a lower frequency, and this is in the infrared. So infrared is also showing some emission, you see two peaks and one peak and so on. Oh, no name is where you don't see any peak at all. Okay? This is what, but black hole in general does explain things very naturally. So how do you test gravity? Well, there are many other options which are consistent. And I explained that in astrophysics it's very easy to get a general answer. You can have the same answer by just playing with different assumptions. So this means that testing gravity is extremely difficult because you can always find a case that is matching the observations because you have fine-tuned the parameters. And there are different ways of doing this through agnostic, so more approaches where you don't make any assumption about the theory, or agnostic approaches where you say, okay, let me check if my model for this black hole of time. On the left, you have a curved black hole simulation. Because we have built this into structure, we can simulate things in curved space-time, but also in area space-time. On the right, we have a dilated black hole, and we have matched the two space-time so that they have the same sort of. At least for those black holes, we cannot rule them out, but we can rule down, we can set some upper limits on the maximum charge. You can do this in terms of speed as well, and again, you take similar results. Many black holes are still compatible, only a few can be naked singularities. Ask, the standard answer to what is it that PhD has done for science, I think PhD has shown that at least for two galaxies, there is a supermassive black hole in the center of this galaxy. This is something that people expected, essentially what you learn when you've taken a strong cosmology course, that at the center of galaxies there is a black hole, but that's a object. If you remember the scientific method that Galileo Galilei has initiated, says if you have a theory, you have to have a prediction, and this prediction has to be compared with the observations. Something that is not very well developed in India, but it would be terrific if we could put in something, say, in Siberia or in Asia, in Japan. But right now, there isn't. Yeah. So we hope to acquire new telescopes. This will increase our network. If we increase the networks, we have longer integration time, and we have also higher resolution variants. So certainly better images.
What do you see in the future? Can we this or can we observe other this black holes? I know it's very difficult, but I want to know your prediction.
We go into space. So you can increase the number of telescopes, you can increase the frequency at which you make the observations. In both cases, you increase the resolution, because if you remember, resolution was like the frequency, the wavelength. But even in the best case scenario, maybe you can get a factor 2 in frequency, and this means that we gain a factor 2 in resolution. If you really want to start seeing other black holes, you need to increase by a factor 4 the resolution. That's when you will start seeing also the other black holes, because they are much smaller. So this will happen not as long as we stick to the Earth. We have to go out of the Earth, we can't make the Earth bigger, but we can send satellites. So we can send telescopes onto satellites, radio telescopes onto satellites, and then we've seen and calculated that if you have a configuration of 3 telescopes, radio telescope with geocentric orbits, not very far, 15,000 kilometers, you can produce in 6 months of observation a gain which is tenfold in the resolution. So this is for you guys to do, convince space agency to fund this mission.
Now we are observing the light coming from the black hole on Earth, right? Now we are observing the light coming from the black hole on the Earth. Now there might be some gravitating object in the middle between this black hole and Earth's spot, right? Which actually deviates the light like trajectory or it affects the motion of the light. It also affects, I think that what we say, the image making.
Yes.
This also should be taken into account in the calculations or when constructing the image.
No, but and the reason why is it's pretty simple. In order to be able, so first of all, the image we see is already the result of lensing. It's just that it's the lensing near the black hole. Now you want to invoke galaxy surface, you know exactly what the galaxy should look like. In the case of gravitational wave, you can do gravitational wave lensing because you know exactly what the gravitational wave form should be. But here, it's much harder because the astrophysics is very complex. So if I have a blob which is fluctuating, I don't know if this is because it's fluctuating because there is gravity near the black hole and there is gravity on the way. So up until we know more about the dynamics near the black hole, it's going to be difficult to disentangle. But yeah, in principle there are also lensing effects on the way.
Did you check if the other object which already well known and has an optical image? That's complete.
But what do you mean other objects?
I mean, that well-known object has already optical image.
But we don't have any optical image of any black hole.
No, black hole. I mean, other object.
Astrophysical.
Astrophysical.
Well, in principle, you can use the NDI for any object that you want. In fact,
And what is fundamental of selecting supplementary observations?
so you
What is the technical use of filtering this galactic biology? So it is a huge limitation of the from the galactic biology.
in a way that the foreground is not difficult because the foreground can be modeled rather easily. So unless you are looking at a flare, you can easily, because you can observe a star all the time, and you know that there is a constant foreground emission. So you can easily take that out. What is more difficult is when you have flaring, in which case, what is the foreground, what is the actual emission. And during the flaring, we normally don't observe because we cannot model the foreground. But otherwise, if the foreground is known, well, it's easy to subtract it.
And I work at the Uzbekistan University. Even if my field is not physics, it was really interesting to explore about the black holes. So my question is, are there any research done that assessing the impact of doing research in black holes to their people's life? I mean, what can it give for the people's life and maybe the impact to the increasing standard of life or maybe for the future generation? This is very interesting to me. Thank you.
That's a very difficult question. The impact that this has on social people, social life is zero. But as zero as it is that of culture, of art, it's the same. It just enriches our lives. Knowledge enriches makes our life more worth living. So although we don't produce a car that makes you faster or whatever, a piece of technology that makes you that simplifies your life, the fact that we know more about the universe is something that makes us richer in dreams. In this respect, I would say it's not exactly zero. It has an impact, but it's very difficult to measure. Okay, I am a very pragmatic person, but at the same time, I want to have a free mind. So while I think all of these observations are pointing towards black holes, I am happy to consider alternatives because one important aspect of science is having a free mind and being open to different ideas. We think black holes are natural. Okay? Everybody, even kids nowadays, know about black holes. But if you think about it, when black holes were first discovered, no one understood them. And those few who understood them said, oh, these are just mathematical toys, they will never exist in nature. It's nature that has shown that they exist, and it's nature that has forced us to consider them as real. So I think we have to have an open attitude towards what we think is happening and what maybe is actually happening in reality. When it comes out to JW's Webb telescope, I think this is telling us very exciting new results about when the first galaxies were formed. Some people are very happy to go and say, oh, this is evidence for violations of what we know. But I would be a bit more cautious there and say, let's make sure
basically you can create a new, longer path for light to travel from the same source to the same destination. So theoretically, what it means is we can observe the same event happening in faraway space multiple times from any such observed places.
So, it's true that black hole bend space-time, but black holes are one-way membrane. You cannot observe other parts of the universe through a black hole because black holes do not let any light come out. What you can do is you can have an object which is similar to a black hole, which is called a wormhole. And a wormhole would allow you, in principle, to see something coming out of another part of the universe, or maybe even a different universe, we don't know. So the question is, have we seen a wormhole or a black hole? All of our evidence is that this is not a wormhole, because a wormhole would behave differently. Wouldn't have a shadow, would behave more like a boson star than a black hole.
We are expanding quite rapidly. So we started the university in 2021 with only 10 faculty and staff members. So today we have almost 250 staff and faculty members. So 40 senior faculty members. So most of them are international. So are they foreigners? Are they people who have the experience in working in different fields? We are very proud of our students. So our student body contains 650 students, and I need to tell you that 60% of them are coming from the residential schools, from the specialized schools, which are specialized in IT, in mathematics, chemistry, and physics and astronomy as well. So in this regard, so we're building here the hub for the of excellent the Technical University of Munich, very intensively, so since we started this project, and also with MIT. So people from MIT are helping us in capacity building. So an important milestone was reached last month when we have organized a huge workshop for many universities of Uzbekistan on the capacity building, on engineering education, together with our colleagues in Nazariy. And also we collaborate very closely with the Cambridge University, so also the Cambridge University Press and Assessment on organizing our admissions. So the Cambridge University members usually travel to Uzbekistan every year to organize our admissions. But overall the globe, we have 400 different partners, so mostly the universities, and we are expanding these partnerships. Since 2021, as we launched the university, so we were very much linked with individuals, the great individuals who helped us, who have a great contribution to the development of the science, technology in the world, but also at the university. For your incredible and great contribution to the development of physics and astrophysics globally, and also for your great contribution to the development of the international relationship of the Uzbekistan Academic Society. So please welcome Professor Luciano Rezzolla.
Between for example, Sagittarius A and then the Earth, the objects between them don't interrupt the imaging.
Because the radio waves, they travel without being absorbed, mostly without being absorbed. They are scattered, so if you take a front of electromagnetic radiation, this front will be a little bit distorted, but it will still propagate.
So you don't take like, so you don't take the picture like just a proper camera like this, just by radio waves, yeah, right?
No, in fact, it's not an optical image. It's an image, but the photons here are optical, the ones that you can see with your eyes. But what we need is radio waves. These are at this frequency. Okay, for that, you need telescopes.
One question has two paths. This one is made by black hole, and clearly it takes some time, some more time. That means there's a delay. Does that mean that we can observe the same event happening here in two different times in Earth?
Yeah, it's just that, in principle, we're not observing this because we don't have the resolution to see this object. We have the resolution to see just very close to this object. And in principle, the light that we observe, if you imagine that this is the disk, there's going to be a jet coming towards us, there's going to be a jet going away from us, there's going to be light coming from the disk. What we observe here is all of it. We get the light coming from the disk, we get the light coming from the jet, we even get the light coming from the other jet. Okay? But all we see is in a rather small area. We don't see background image sources.
So it's very distorted.
It is very distorted. The lensing here is very, very strong. Okay? Yep. Radio waves of the matter that is falling near the black hole. The matter near the black hole, as it gets closer to the black hole, becomes dense and hot, and so emits light. And this is the light we see. Okay?
The second question. The center, because of the huge mass, we cannot take the picture, image of the center.
Of the event horizon, yes.
So, there's the countries where other professors focusing on new technologies to take the more clear photos. So what kind of technologies are they planning with you?
This is a collaboration. So, essentially all the interested scientists in the world are part of this collaboration. And if someone wants to be part of the collaboration, he can just apply and be admitted. So it's a very open system. Anyone who can contribute, or wants to contribute and spend time in doing this research is welcome. But the improvements is not that there is a competing project that wants to do better. It's all of the ones who want to do are under the same umbrella, under the same collaboration. And you're right, we can't see the event horizon. By definition, the event horizon cannot emit any light.
Your future is with Kazakhstan. So please be close with Kazakhstan. Without Kazakhstan, you will not create a good node. In order to construct good node, we need to be very close with Kazakhstan as soon opportunity came. So in Uzbekistan, we started to have change September 2016. And in September 2016, more than 10 people were in Al-Arabi and Istanbul. So we took this opportunity immediately. So now I cannot imagine my life without Kazakhstan. Usually I used to visit Kazakhstan at least once or twice per year. So we have very good collaboration with Al-Arabi University. So we have weekly seminar on reytingida astrophysics, and it makes us so I say Uzbek has semi-society, and semi-society is coming from Kazakhstan. Let us combine it and make one society. So now we don't have any border with Kazakhstan, so it is one node. But one node cannot exist globally, so we need to have more interaction with foreign communities. So with Europe, especially what I would like to say is that I'm very thankful to Abdul Salam's International Center for Theoretical Physics when I first time went there in 1995. So I met Dennis William Sharma. So Sharma's idea was to expand relativistic astrophysics through the whole globe. So fortunately, he was the person who made me familiar with Luciano Rezzolla, and we are almost 30 years we are in contact. So I'm very thankful to ISTP and hissasi. So I think the development of relativistic astrophysics in Uzbekistan is totally connected to Trieste. So Trieste made very good input to development of this subject, and I think the connection with Inter-University Center for Astronomy and Astrophysics in Pune also came through Trieste. So Trieste played very important role. So then I say that we need to tribute to Abu Salam, and I say that the next conference I discuss this issue with akademischen Kadir Bulanov, akademischen Strategie.
Honorary Professor Academicians, it's a great honor for me, and I'm pleased to be here, to be invited and talk to you, make plans. I was not warned about this, otherwise I was my jacket maybe, huh? It's just but I hope, yes. Yes, it's spontaneous, and I like it. And yes, and there's actually, you already, I mean, you said already so many things which I would also like to support and say, but so please allow me first to say a few words about myself before I come to this collaboration issue. So, unfortunately, that I am since 2009, my official title is a special state foreign expert in China. It's called Whiteboard Chuanjia for those maybe Chinese. And since that time, I am working in Beijing at the Chinese Academy of Sciences, the National Observatory, and also in Peking University. So since that time, China is my second affiliation, which is just missing here. It's always both. Yeah, I don't break with Germany. I just still work partly in Germany, partly in China. So that is a Silk Road connection. Yeah, but let me say, I am 100% convinced and absolutely clear that Uzbekistan belongs to the Silk Road. There's absolutely no doubt about it. And it's really just this due to individual history of our collaborations in China. We had collaboration with Korea, with Seoul National University, and with Kazakhstan actually. Fesenkov Observatory, the current director has worked with me as a young postdoc